I'll just press record. So I should say I'm recording this this talk, so I'll try and share it with people later for those that couldn't make it. But today we have Bill Chadwick from Oregon, and he is going to talk to us about long-term deformation monitoring at Axial Seamount in the North Pacific. Bill got his PhD in geology from the University of California, Santa Barbara. It's a very nice place indeed. Modeling ground deformation observed in the crater of Mount St. Helens after its 1980 eruption. And after a postdoc with the USGS studying Galapagos volcanoes, he took his study of volcanoes into the oceans and began working with Oregon State University and the NOAA on hydrothermal vents and submarine volcanism in Newport, Oregon, where he's worked for the last 32 years. So I'll hand over to Bill take it away.
All righty. Let's see, share my screen here.
Yeah, got it.
Okay, good. Well, thank you very much for inviting me to talk and for being here. Wish I could be with you, but this is the next best thing, I guess. Okay, so let's see. First, I want to acknowledge.
Coupez les micros, s'il vous plaît.
Sorry, Bill, I've just muted you by mistake. Just bear with me 1 second.
Okay, now I'm unmuted.
Yes.
All right.
There we go.
So I want to acknowledge a bunch of co-investigators. We've done a lot of this work with Scott Nooner, Dave Caress in particular. I'm going to show some results from repeat mapping with AUVs, and Dave Caress has done all that work. I'm going to show some seismicity from Axial, which is the results from William Wilcock at University of Washington. And some of the data I'll show is from the OOI Ocean Observatories Initiative Cable Observatory at Axial, which is led by Deb Kelly. That's a lot of work there they put in at University of Washington for the broader community. And also want to acknowledge funding from the National Science Foundation in the US. So here is an outline of what I'm going to talk about. So I'll talk about how we measure deformation at Axial Seamount, and then the results we have to date from modeling that deformation. And then I'll look at the relationship to the seismicity we see, the evidence for changes in magma supply, and the implications for eruption forecasting. So first, just to orient you a little bit, on the right, let's see, here's Washington and Oregon and the northwest coast of the United States. I'm here in Newport. About 500 kilometers offshore is Axial Seamount on the Wantafuca Ridge. Wantafuca Ridge is a spreading center, so it's plate boundary where the plates are spreading apart. Here's the Cascadia subduction zone along the coast, and a Blanco transform fault down here. So if we looked at a cross section, it would look something like this. Here's the subduction zone, the Cascades. Here's Axial Seamount out here with where the plates are spreading. And here's a little movie of what the seafloor looks like with the ocean removed. This is bathymetry, so we're zooming into the top of Axial Seamount. It's got a south rift zone and a north rift zone that are parallel to the Wantafuca Ridge. And at the summit, it's got a caldera that's 3 kilometers across, 8 kilometers long. The walls are about 100 meters high, and the depth of the seafloor here is about 1,500 meters. It's an interesting place to study because it's very active. It's had 3 historical eruptions that we know about. In 1998, it erupted lava flows on the South Rift, and we know that seismicity extended down the South Rift zone about 50 kilometers. So we know a dike intruded down there from the summit. In 2011, It was similar lava flows in the caldera along the upper South Rift, but this time it erupted lava way down on the South Rift, about 30 kilometers from the summit. And in 2015, it went the other way. It erupted lava flows up the North Rift zone. So now we'll look at deformation and how we measure it at Axial. So, there's many volcano monitoring techniques, and deformation is just one of them. So Axial is a basaltic shield volcano with a summit caldera, and at volcanoes like this, often they have a cycle of deformation where there's inflation between eruptions, and then during eruptions you get deflation. So inflation between eruptions, sudden deflation during eruptions when the magma is removed from this reservoir where it had been accumulating. And so at volcanoes like Krafla in Iceland and Kilauea in Hawaii, sometimes you can get a very repetitive pattern. So here we're measuring inflation, gradual inflation leading up to an intrusion or eruption, then sudden deflation. And sometimes it can be this sawtooth repetitive pattern. And you can see that this could be a way of anticipating when the next event might occur, which we've tried to do at Axial. On land, you measure deformation with leveling or GPS or satellite interferometry. And of course, on the ocean floor, none of those work. So what we've done instead is primarily use pressure sensors to measure the vertical movements of the seafloor. So if the seafloor moves up during inflation, then the pressure that's measured by these sensors decreases, because basically there's less height of the ocean above it. And the opposite occurs if you get deflation, you measure more pressure. So on the left here is what some of these look like. We've got a whole stable of different sensors, but they all more or less do the same thing. So they measure pressure, we convert the pressure to depth, we remove the tidal signal, and the standard bottom pressure recorders, these pressure sensors, are great for detecting short-term movements, but they have long-term drift that you have to deal with somehow if you want to do long-term monitoring. And it's a problem because the size of the drift can be the same as the signal you're trying to measure, the volcanic inflation. So the way we've dealt with this is we've also used this, what we call a mobile pressure recorder. So it's the same sort of pressure sensor. We connect it to an ROV, and we make measurements at a series of seafloor benchmarks that we've put out. And so we measure these. So this is like a campaign mode kind of survey every 1 to 2 years. We get the relative depths of the benchmarks to about 1 centimeter. And we've got one reference benchmark that's located 10 kilometers outside the caldera that we assume is stable. And then we look at the displacements of the other benchmarks in or near the caldera. So this helps us get around the drift problem and enables long-term monitoring. In addition, in 2014, this fabulous thing called the Ocean Observatories Initiative cabled array became active. So it's a fiber optic cable from the Oregon coast. One strand goes all the way out to Axial Seamount. This is operated by University of Washington and funded by the National Science Foundation. And out at the summit of Axial, the cable comes in and there's a bunch of instruments connected to it, including these 7 seismometers circled in blue and 4 bottom pressure recorders circled in red, and you can see one of those in the upper right there. So this also enables long-term monitoring, but also gives us real-time data, which we've been trying to take advantage of. So I'll talk more about that later on. But so here's our current array of basically pressure monitoring stations. So the black lines are the cable coming in, and the red dots are the cabled instruments. The white dots are where we have all the benchmarks, where we make the ROV based measurements every few years. Here's our reference station down here outside the caldera. At all of those, we also have these green dots, which are continuously recording pressure recorders. So we have both continuous data at all of our benchmarks also. And then there's some extra ones. These blue ones are deployed and recovered by ship as short moorings. So just to expand the array. So next I'll show a time series from the center of the caldera here, which is our longest lived site. So now we're going back 20 some years, back to 1997. And on the y-axis is the change of seafloor elevation in meters. So several things to point out here. So first of all, here's our three eruptions: 1998, 2011, 2015. In each of these, the seafloor dropped. This is 3.2 meters. These two are 2.5 meters. So you can see the range of the deformation is quite large, which helps us in a lot of ways, because we don't have to worry about noise and being super precise in many ways. Also, excuse me, the pattern appears to be fairly repeatable. There was a data gap here, so we don't really know how this ties in to the rest, but all of this is tied together by the ROV measurements. And so for example, the inflation threshold that was reached before the 2015 eruption was about 30 centimeters higher than in 2011. So fairly repeatable, but not exact. And in fact, we use this pattern to forecast both of these eruptions. The forecast for this one was pretty wide, but the rate of inflation was quite high between these two eruptions. So we were able to forecast that this eruption would happen sometime in 2015, and it did. And we're trying to do the same thing going forward, which I'll talk about at the end. Something I just mentioned is that the rate of inflation has varied quite a bit. Basically, the slope of this line, you can see how much it's changed, and I'll talk more about that as the talk goes on. So that's sort of how a look at how the deformation has evolved with time. I also want to talk about what it looks like in space, measured at different places. So in the upper left here, we had two BPRs out to measure the co-eruption deflation during that eruption. Then here's the inter-eruption inflation over the next 10 years. These are the ROV measurements at the benchmarks. Here's co-eruption deflation during 2011, again at two sites. Then we basically over time, we were adding more and more sites. So we have more and more measurements with time. Here's interruption inflation from 2011 to 2013, co-eruption deflation in 2015, and the same thing, but over a longer period of time, 2 years at all these benchmarks. So this time period, we have the most measurements in terms of space. So we've done a lot of modeling with this data set. And so since it extends from 2013 to 2015, it includes some pre-eruption inflation, a big deflation during the eruption, and then a little bit of inflation afterwards. So that's why the numbers are smaller here than here. All right, so now we'll talk about how we've modeled this deformation. And, the aim here is basically to figure out what's going on under the volcano, what the magma storage system looks like, what geometry it might have, what depth, volumes that move in and out and so forth, and whether there's a batch of red food coloring anywhere. So our approach has been to keep it pretty simple because we've only got measuring points. We only have limited observations, so we can't constrain elaborate models. So we've looked at three different models and to see which is the best fitting, which agrees best with the observation. So one is the point source that was published long ago by Mogi. One is a spheroid that can be dipping in any direction and has two axes that can vary in size. And then we've looked at a sill source, but a penny-shaped crack source. So all of these have limited parameters that we can try to solve for and see what fits the observations the best. So among those models, for the 2013 to 2015 deflation associated with the 2015 eruption, the best fitting model was a prolate spheroid, steeply dipping, with a centroid at about 3.8 kilometers depth. So the centroid is here, this yellow dot. These contours are the predicted deflation from that modeled source. The arrows compare the observations in red to the model predictions in blue. And this is a cross section from 0 to 6 kilometers east-west. And this is a north-south cross section with the same, just to show what the orientation of this in those two dimensions. And in the lower right is a comparison of the data in red and the model predictions in blue. So the fit is pretty reasonable. So just to compare that with the seismicity observed at Axial, this is data from William Wilcock. So all these dots are the earthquakes observed before, during, and after the 2015 eruption. You can see most of them are along the eastern boundary, caldera boundary fault, some along the western fault, and they're in two outward dipping zones. And the pattern is the same before, during, or after the eruption. The earthquakes stay in those same locations. And the way this makes sense is that for a caldera, this is a sandbox experiment just showing faulting typical during caldera collapse. There can be these outwardly dipping faults connected to the inward dipping faults. So apparently at Axial, these faults in red are seismically active, whereas the ones in blue are not. But what's interesting is that these faults move during both inflation and deflation. So during inflation, before the eruption, these are focal mechanisms showing the sense of slip in these earthquakes. It was mostly normal fault slip during the inflation phase, and then it reversed to mostly reverse slip during the co-eruption deflation. So the faults basically reversed their sense of slip. And that study also showed that the slip on the faults was substantial and probably was contributing to the surface deformation. So our next modeling study here by Hefner and others, 2020, was to try to take that fault slip into account. So here's the original model that we published in 2016. and here's the results from the Hefner modeling. And what they did was they took the fault slip estimated from the seismicity and calculated the deformation that was predicted from that fault slip on these two caldera faults, and then subtracted that from the observations, and then looked at what the best fit model to that to those observations with the fault slip removed would be. And they came up with a similar best fit model, another prolate spheroid, this one in green compared to the original one in red. And it's similar, steeply dipping, but the location of the centroid moved about 2 kilometers to the southwest. So, and this is the predicted displacements from that. So in addition, another way of measuring the surface deformation at axial that we've been adding into slowly for about the last 10 years is using repeat bathymetry from autonomous underwater vehicles. Here's the Sentry AUV operated by Woods Hole. This is another AUV operated by the Monterey Bay Aquarium Research Institute, MBARI. And these are the latest results from that work, which was presented at the AGU meeting by Dave Caress. So these are depth changes from 0 to 2.3 meters between bathymetric surveys in 2015 and 2020, so over 5 years. And basically it confirms that all of our pressure measurements are kind of confined to the southern caldera, but these extend much further out. And they confirm that, you know, the maximum uplift is at or near the caldera center. And these are 3 cross sections of the displacements. This cross section is along this line, northwest to southeast. This cross section is from southwest to northeast, and this cross section is from north to south. So you can see they all have uplift that's maximum near the caldera center. But a much different picture comes from multi-channel seismic results. This is data published by Arnulf et al. In 2014 and 2018 from a survey in 2002. And what they found was they imaged a magma reservoir underlying the whole caldera, and in fact extending north and south quite a bit, a little bit offset to the east. So this is a cross section along this northwest southeast line, JF 61, and this is a cross section from JF 63 along this line. And this is depth below the seafloor. So the top of this thing is 1.5 kilometers, and the bottom's at about 2.5. And they, from the strength of the returns, they interpreted that there was a high melt region beneath the southern part of the caldera, and the rest of the reservoir was mainly crystal mush. So, you know, that's quite different from the deformation model we got, which was a steeply dipping body, whereas these seismic results are kind of a horizontal cigar-shaped body. So those seem quite different. And so we've thought a lot since then of how to make sense of those two things together. And our latest thinking is that, well, these are some more multi-channel seismic results from Carbat et al. 2020. So in addition to here's the blue outline of the bigger shallow magma reservoir. they looked at the same data set, but looked deeper in the crust and found that there was a series of stacked sills below this southern part of the caldera outlined in red here, extending from about 2.5 kilometers to maybe 4.5 kilometers below the seafloor. And they compared this to our deformation model results. Our original model is this green prolate spheroid, and the arrows point to where it would move in the revised model that took faulting into account. So that actually moved the deformation model within this field of the stacked sills. So our current thinking is that maybe the deformation is caused by a deep magma conduit that's in the core of these stacked sills. So maybe that's how the two things make sense together. So here's the AUV bathymetry results again, and with the multi-channel seismic outline in blue here added, the sill outline in red, and then the revised model centroid, this green dot, kind of barely in that area. And if the preliminary results from modeling these displacements from the AUV repeat bathymetry gives a similar best fit model somewhere around here, maybe a little bit further north. So, just wanted to kind of back up and say some things about these models. So that the original model, the appealing parts is that, the model centroid, which was on the east side of the caldera, it was appealing because that's where most of the earthquakes occur. It's also near where the high melt zone was in the shallow magma reservoir. And it was where all three eruptions have initiated. They've either gone north or south from somewhere on that near the east edge of the caldera. But of course, that model was not highly constrained and is certainly not unique. So the revised modeling that took faulting into account, the pros include that it actually fit the observations better than the original model. And it also appears to fit the AUV data. Some cons might be that, so far we were looking at a kind of a wide time window that included a lot of different deformation and a lot of different faulting. So that maybe is not so appealing. And it also, we observed that right after an eruption, there's hardly any earthquakes. So another question is, well, how does this model work when there's few earthquakes, but there's lots of deformation happening? Maybe is there aseismic slip on the faults in those first years after an eruption? And of course, our limitations are that the pressure data is precise in about plus or minus a centimeter, but limited in the number of observations, whereas the AUV data are broad, but they're less precise, about plus or minus 20 centimeters. So neither of those can tightly constrain a deformation model, but they're better, better together than separately. We've only tried relatively simple models so far because we don't think we can constrain anything too elaborate. And so far, we don't really have great constraints on the fault slip either. But there's some things that we think we know pretty well, that the maximum deformation is consistently at or near the center of the caldera and not in the south over where those stacked sills are. So that's pretty clear. And so this either requires a northward dipping pipe-like source like our deformation models, or multiple sources, which we haven't tried so far. Also, the depth of the source must be deep, and by that I mean, with a center at 3 or 4 kilometers depth. For example, we've tried sources that are just at the depth of the shallow reservoir, and those cannot explain observations. So so we need a source that's fairly deep beneath the caldera. And the pattern during inflation and deflation are coming from the same source. That's also pretty clear. If we model a period of inflation or deflation, we get very similar results. And here's an example of that. This is the co-eruption deflation we've been modeling, and here's the inflation that's occurred for the last 5 years. And the maximum displacement is always at the center. The minimum is always to the east here. And the others are in between. All right, so now I will talk some about the relation to seismicity and these other things. So, so using data that we get from the Cable Observatory, we've found that we get a clearer picture of the geophysical signal we're interested in, the volcanic inflation, if we do some differencing. So here, these two plots are from these two bottom pressure quarters. This one's at the center and it inflates the most. This one's on the east rim and it inflates the least. And so you can see on a sub-daily period, there's noise from tidal residuals. So that's the part of the signal that's not taken out by our tide model. But you can also see over days to weeks, there's kind of a undulation that's common in both of these stations. And this is an oceanographic effect that's basically due to weather and the ocean sloshing around. But it's common to both stations. So what we found is if we subtract this station from this station, it takes out most of that noise and we get a much clearer picture of the geophysical signal we're interested in. So for the rest of this talk, I'll mostly be showing this differential pressure data. First, here's what the seismicity looked like leading up to the 2015 eruption, hundreds of earthquakes per day, then 1,000, then several thousand in the months leading up to the 2015 eruption, when there were thousands and thousands. And then immediately after the eruption, it dropped off. And here's a zoom into a level, maybe 10 earthquakes per day. And here's a little wider view of that. Here's the 2015 eruption, thousands of earthquakes, then just 10 earthquakes per day or so for several years to about 2018. And then the number of earthquakes slowly started to pick up, but it's been kind of variable. So superimposed on that is this differential pressure signal. So here's the big deflation in blue during the eruption, reinflation, and till about late in 2020. And so I'm going to zoom into this part of the record from 2017 to 2020. Here we are. And now in gray are periods when there was no seismic data for various reasons. And you can see there's several steps in the reinflation record. And there's been a series of these. Here I've identified them, the beginning of each one by these red lines, these short-term deflation events. And you can also notice that immediately after these, there's a drop-off in the level of seismicity each time. And this is especially obvious if we zoom into one in particular. So we're going to zoom into this one in June 2018. Here's the differential BPR data. We're inflating till here, then it deflates 2.7 centimeters over 18 days. then starts reinflating. And this third line is when it reaches about the same level as the level where it began the deflation. And here's the same time period, now a histogram of earthquakes per day. There's the beginning of deflation, the number of earthquakes drops down, and it doesn't come back to the same level until it's reinflated to about the same level. So this is, we see this over all of the short-term deflation events. So what is this, what's happening here? So if we envision this shallow reservoir with a bunch of stacked sills below, and during inflation, we've got magma coming up through this zone where it's surrounded by some partial melt zone that's maybe viscoelastic. So during inflation, there's increased pressure in here, it's pushing up, it's driving the earthquakes in the faults above the magma reservoir. So one hypothesis is that these short-term deflation events could be from magma either leaking into one of the rift zones or a satellite magma body from the shallow reservoir. But if that were happening, we would expect that we might see inflation somewhere else, or maybe earthquakes, changing location. And basically, we don't see that. This is a study by Audra Sawyer, who presented this at the AGU in 2019. And she looked at this same short-term deflation event and did some modeling of what the source of the deflation was, and basically came up with this a very similar model to our previous model. So it wasn't a different deformation source. And if we look at the seismicity during this same deflation event, here's the earthquakes for about 3 or 4 weeks before it started. Here's the earthquakes during 18 days while it was deflating. So the number of earthquakes goes way down. Here's the earthquakes during the reinflation phase before it came back to the same level. And then here are the earthquakes for 24 days after it had attained that level of inflation. So you can see the pattern of earthquakes pretty much stays the same. It's just that fewer earthquakes are happening during the deflation event. So it's not really changing location. So an alternative explanation is that during these deflation events, basically the magma supply is interrupted to the shallow reservoir, and we've got some sort of porous flow and viscous relaxation going on that is causing the deflation and basically a shutoff of the pressure that's driving the earthquakes. And so the same sort of things happening during all of these. The May 2019 was similar but different in that we had the deflation, the shutoff in seismicity, but then we had 2 months where it was flatlining, it wasn't inflating or deflating, low seismicity. And then since then, it's been inflating at a reduced rate, maybe half the previous rate. And if we look at all of these short-term deflation events, you can make a case that the rate of inflation between each one is maybe different. So each of these deflation events maybe changed the inflation between some of them, or certainly after the May 2019 one, it's definitely gotten slower. So if we zoom out to the full record, we can also see that the rate of inflation has changed a lot over the whole 20+ year record. So it was about 15 centimeters a year over this long time period in the early 2000s. It increased to about 34 centimeters a year leading up to the 2011 eruption. Between 2011 and 2015, it was quite high, 67 centimeters per year on average. The reinflation phase was about 50, then it slowed to 30, and now we're in this relatively slow rate again. So looking over this entire period, you can argue that this reflects a surge in magma supply at Axial Seamount that included this time period when the 2011 and 2015 eruptions occurred, and probably explains why they occurred so close together, because there was a lot of magma coming into the system. And now, since 2015, we're in this waning magma supply phase, and maybe that is explaining these temporary interruptions in the magma supply. So this also is affecting our efforts to forecast when the next eruption is going to occur. In early 2019, before that May 2019 pause happened, the rate was quite high. So we're just extrapolating the rate of inflation into the future and noting when we're going to get to the 2015 threshold, and maybe another threshold that's a bit higher. So we had a forecast window of 2020 to 2022 then, but then the May 2019 event happened. We could see that the rate was slowed. We didn't know how long it was going to last, so we expanded the forecast window. By late 2020, we could see that slower rate was continuing, so we pushed the forecast window out further. And now in mid 2021, it's even slowing some more. So we keep pushing our forecast window further into the future. So we don't know if that's going to stay the same, if it's going to slow down, speed up. So we'll just have to keep monitoring to find out. All right, so here are my conclusions. So the best fit model of the observed deformation at Axial is a steeply dipping pipe-like conduit that's possibly in the core of the seismically imaged stack sills. By using this differential BPR data since the 2015 eruption, we've seen these repeated short-term deflation events associated with changes in inflation rate and a simultaneous drop-off in seismicity. We think that these may be a consequence of the waning magma supply since that eruption, following an apparent surge in the supply. And even though Axial is now reinflated about 85% of the level it reached before the 2015 eruption, we know the rate is slowing and the next threshold may be higher. So we're still several years away from the next eruption, we think. And our current forecast is wide and poorly constrained because the inflation rate is quite slow and variable. So we kind of have to just wait and see at this point. So, and I wanted to end with just a few URLs where there's data from Axial Seamount online. I've got this website that posts near real-time data from the OOI cabled array from our pressure sensors here. I've also got a blog of our attempts to do eruption forecasting. William Wilcock has displays of the seismicity from Axial, also from the cabled array, and in general, more data from all the OOI sensors is available at this website. So I will stop there, and I would welcome any of your questions.
Okay, good stuff. Well, thanks a lot, Bill. That was really interesting. If people have got questions, could they just write a message in the chat and say I've got a question, and then we can go to you and you can unmute yourself and ask the question. So Satish has a question. Go ahead.
Yes, Bill, very nice talk. Thank you very much. It's very, very clear. If I remember correctly, you said that the source was deeper, 3 to 4 kilometer depth, whereas the magma chamber, the upper one, is 1.5 kilometer. So any uplift has to happen above this magma chamber, not in the lower crust. How do you explain this? I did not get that clear.
Yeah, so it's a little non-intuitive to me, like when the multi-channel seismic survey showed this big reservoir, under the whole caldera, and almost horizontal, it seemed like, if there's a lot of melt in there, that would be transmitting pressure and causing deformation. But we've actually tried, a model that's shaped like that reservoir, like a horizontal cigar shaped thing, and it just doesn't fit the observation. So somehow the pressure that's causing the deformation we observe at the surface is coming from deeper in the supply system. And, we're envisioning that maybe the core of this system has a conduit that's maybe especially melt rich, and that's where most of the pressure is transmitted from, and that somehow in the shallow reservoir, maybe a lot of it is, is mostly crystals and not so much melt, and so it doesn't transmit the pressure either at all or on a different time scale, or yeah, so it is a bit of a disconnect, and it's, we've scratched our head a lot to try to reconcile the two, and that's, this idea of a conduit causing the deformations is our best guess, basically. Did I answer your question?
Sort of. The question is, could it be at the Moho depth?
Oh,
I'm missing
not
it.
that deep, no.
How thick is the Moho there, crust in that area?
I don't know off the top of my head, but I would guess it would be, 8 to 10 kilometers. So that's quite a bit deeper.
I don't, has he answered your question there, Satish?
Yeah, I'm fine. Thank you.
I'm curious, Bill, about the model. I mean, you kind of touched on it there in your question with Satish, but you obviously came up with the sort of elongate spheroid shape. I can't remember how you described it. Sorry, but I was wondering if there was. You said that was the best fit model. I was wondering if there was any. If there's any possible other alternatives in your models, and what the kind of errors on those would be, and if that would change the interpretations at all.
Yeah, it certainly could. I mean, we've only looked at these three fairly simple models, and one thing I forgot to mention was, one reason the prolate spheroid model is consistently preferred among them is that, it's of those three, it's the only one that can have a dipping source. And so that can generate a non-axisymmetric pattern of uplift at the surface. And the other two are axisymmetric. So, I think the observations are not axisymmetric exactly. And so that could be one reason why this dipping source is preferred. So there's certainly other, source models you can envision that might explain the deformation. That, one thing I've wanted to try and haven't done yet is, maybe a series of sills that where the deeper ones are further north compared to the southern ones, something like that. So it's kind of simulating this northward incline to the pressure source, but maybe using sills instead of this cigar shaped thing. We haven't done that yet, but yeah, one problem is that the fancier you get, the more it's you're introducing your own imagination and bias, and you know, you don't, the data can't necessarily constrain
Yeah,
things too well, but at least you can see if how it might fit the observation. So I think it's worth doing.
yeah, because there was just a red cross on the dike model, but I think you mentioned at the beginning that you'd seen some diking to the south or something.
Right. Of course, that's just during the eruptions when this rapid deflation is going on. So yeah, and those diking events that feed the eruptions, you know, wouldn't be explaining, you know, the big
Yeah.
pattern of inflation between eruptions, for
Yeah,
example.
yeah, of course. Satish, I was thinking something similar actually, but you got another question there about land volcanoes.
Yes, my question is, Bill, how do the results compare with what we know on land of volcanoes? And can we learn anything from those observations, because those are much more prevalent and we know more about them?
Yeah. Well, there does seem to be more and more evidence of stacked sills in the crust, but on land they tend to be deeper, like in the lower crust. And one thing that's different about axial is it's superimposed on the spreading center. So, you know, where the crust is quite thin because it's being generated right at the ridge axis. And so I think axial is maybe unusually shallow and maybe simple because what complicates deformation at a lot of land volcanoes are, you know, thick crust and interactions with other volcanoes and landsliding, and you know, there's many other things going on in some places. So I think in some ways axial is sort of a simplified system, and that's maybe why we've been able to do some eruption forecasting, is because there's not as many confounding processes going on. But in some ways, it's, you know, the axial system is similar to Kilauea and Krafla in that, you know, you're getting magma accumulation below the caldera till it reaches some critical point, and then it injects a dike down a rift zone away from the summit. So that sort of pattern is still evident. But yeah, we're because it seems repeatable, we're trying to you know, see what we can learn about eruption forecasting there and what works and what doesn't.
Taking that further, what about the lateral extension happening? As you say, we are at the spreading center. So you have a 53 millimeter per year or something like that extension happening.
Right.
And what is the role of that in inflation diffusion?
So far we don't have, let's see, we don't have any horizontal deformation measurements. We did for a short period, but that ended, and there people are proposing to install that as in the future. But yeah, so we don't have any direct measurements, but one thought is, you know, one reason why the 2015 eruption intruded north instead of south was because we had the last two had gone south, and you know, if you inject dikes along the spreading boundary, then you're relieving some of the extensional stress, and it, you know, maybe it had obviously been longer since it had gone north, so it was more favorable to have the dike intrude that to the north. So there's thoughts like that, and certainly the, you know, the plate spreading must is part of the story that we haven't really paid too much attention to, I think, because it seems like the magma supply system is the driver of when eruptions occur, rather than, but certainly they're linked.
Thank you.
Unmuted. So Jay, do you have a question?
Yeah. My question. Thanks for your talk, and I have a question. So in your pressure data, there is a higher mass supply during 2015, about 2015. So my question is, the eruption step during the high mass supply phase and during other times. So there is any difference in lava morphology and the eruption step? Yeah.
So the question is, was there a difference in the lava morphology in 2015 compared to the earlier ones? Is that right?
Yeah, because it's a higher mass supply.
Not really. So the 2015 eruption, there was a higher volume of lava extruded. I meant to check these numbers, but I didn't. But I think the volume of the 2015 eruption was something like 150 million cubic meters, or 0.15 cubic kilometers. But 90% of that was in the lava flows that were furthest from the caldera, the ones further north. So, and that's this pattern we've seen in all three eruptions, where the eruption starts in the caldera. It's must be at a fairly high eruption rate. So it's mostly causes thin sheet flows in the caldera. But as the dike propagates either north or south, and more deflation happens, the driving pressure in the dike probably gradually decreases as it extends. And so a few kilometers outside the caldera, you start to get pillow mounds instead of thin sheet flows. So the lava flows erupted furthest from the caldera are these thick pillow mounds that are up to 120, 30 meters thick, whereas the lava flows in the caldera are, just at 10 meters or less thin sheet flows. So that's a pattern we've seen in all three eruptions.
Okay, thanks.
Cool. Okay. Lastly, Natalie, did you say you got some questions?
Thank you, Bill, for this very nice talk. I have a question about the seismicity, because the seismicity is always along the one part of the caldera and not in the north and in the south. So I would like to know if you have some feeling about that. Do you know why?
Part of it could be where the seismometers are. Let's see, maybe I can go back to a slide here to show this. Let's see. Let's see here. Yeah, like if we look at this, so the black dots here are where the seismic stations are.
Sorry, Bill. Can everyone see the screen there? I can't see it. I don't know if.
Oh, you can't?
We can't see the screen.
Oh no! Why didn't that happen? Maybe I didn't share my screen. That's why
It came up, it came up, and then
I was showing it to myself.
it.
Okay, how's that?
Yeah, there we go.
Sorry about that. Okay, yeah. So here's a map of the seismicity. these black dots are the seismometers. So they're kind of, so most of the earthquakes are in the vicinity of the seismometers. I don't know. It's, you know, I'm not a seismologist, so I'm just guessing, but yeah, it seems like most of the earthquakes are along the east and west caldera faults, and not so much in the south, although there are some in the south here. You can see them kind of wrapping around. This dotted outline, by the way, is the outline of the deep sills. So they kind of extend beyond that. And this plus is kind of the center of the sills, supposedly. And these X's are our two deformation models. So this was without the fault, without considering the faulting, and this is with considering the faulting. So, and this is, you know, William Wilcox quick processing of the seismicity. There's also been a couple of papers looking more closely at the seismicity and doing more precise locations. And they've seen some evidence for faulting on the inward dipping faults, but you know, most of the seismicity is on these outward dipping faults, and it's more or less the same pattern. So I don't know why it's not more circular. You know.
It seems that it is oriented like the regional fault along the Juan de Fuca Ridge, no? It's a little bit, it's not the same, almost the same. It is not controlled by the regional tectonics. No?
Maybe. I mean, it's hard to say because axial's maybe 1,000 meters tall, you know, built on top of the Juan de Fuca Ridge. The South Rift Zone comes up through here, and then, you know, some of the eruptive fissures for the 2015 eruption kind of started here and went up on the northeast rim and fed this flow and then jumped over. So the diking that feeds the eruptions is sort of along this east side. I think, you know, that Axial is a hotspot volcano that's superimposed on the Juan de Fuca Ridge. I probably failed to mention that. So it could be the interaction of the hotspot and the ridge. So the main part of the ridge is way off to the east, whereas in the hotspot, I think is migrating east towards the ridge. So that could be an influence that, you know, the hotspot is a little bit east. You know, the magma supply is a little bit offset to the east compared to the center of the volcano. But I don't know, that's kind of speculation.
Okay.
Do you have any seismicity linked to the dike propagation, the way they have seen in Iceland and Ethiopia?
Seismicity related to dike propagation?
Yeah.
That there certainly was a lot of seismicity during the dike intrusion and eruption in 2015. What was surprising to me is they didn't really see a distinct, you know, most of the seismicity was still on this outward dipping plane. So I don't know if that means the dike intruded up through that and to the surface or what. It's also a little bit complicated because there's so many earthquakes during the eruption that, you know, they can't locate all of them. And so I think some of the story, and especially farther away from the instruments. So I think some of the story during the eruption could, you know, is hard to actually detect. So Yeah, and because most of the instruments are inside the caldera, they couldn't really follow the propagation of seismicity to the north.
Okay, I think is that everybody's? Yeah. Okay, great. That was excellent. That was excellent, Bill. Thank you very much, and some good discussion there as well. Yeah, I can't remember off the top of my head when our next seminar is. I think it's in a couple of weeks. But you will obviously send an email. So yeah, thanks again to Bill, and yeah, see you all in a couple of weeks. I'll send an email. I've recorded this for anybody that wants to see it. So I'll send an email around with a link to the recording once I've got that. Okay.
Thank you very much. Bye.
All right, thank
Thank
you.
you very much.
Yeah, thanks again, Bill.
Bye.